The search for proton decay has yielded remarkable results over the past 50 years, with the next generation of experiments, Kamioka and Dune, exploring the range of lifetime from 10 to the 34th to 10th to the 35th years. However, if the proton lifetime is beyond the reach of these experiments, the field is in urgent need of new ideas. The path of building ever larger actively instrumented detectors with sufficient mitigation of correspondingly larger backgrounds is reaching a point beyond which it seems unfeasible to proceed at any reasonable cost. We discuss the possibility of using paleo-detectors to search for proton decay. If one measures the lattice damage caused by the products of a proton decay in a 1 billion-year-old mineral, a 1 kilogram detector would suffice to match the future expected megaton-year exposure of Dune and Kamioka. In principle, the signature of proton decay in a paleo-detector could be rich, a few micron long, high-density extract from the nuclear remnant and additional lattice damage from the charged proton decay products. In light of radiogenic and cosmogenic backgrounds, however, the lattice damage that might be produced by charged kaons from proton goes to nubar K plus decays at the end of the kaon's range appears to be the only feasible signature. Sufficient suppression of the irreducible background of charged kaons produced by atmospheric neutrinos in terrestrial paleo-detector samples requires that such an experiment must be conducted using samples from the Moon. For the charged kaon background arising from cosmogenic muons to be suppressed, lunar paleo-detector samples must be extracted from depths greater than 5 km. Given the current push to return to the Moon, sourcing minerals from such depths seems less far-fetched than a first impression would suggest. In order to gain a deeper understanding of the thermal annealing and mobility of vacancies on geological timescales, a dedicated experimental program must be conducted. A microscopy technique that is capable of efficiently reading out these damage features with particle discrimination in macroscopic volumes is required. Minerals which are both common on the Moon and susceptible to the formation of color center defects that can be read out using fluorescent microscopy techniques, for example olivine, appear to be the most promising for paleo-detectors.